All right, we have some great speakers here, so we're going to go ahead and get started. My name is Bob Finch. I am president of Select Spectrum, and I was pleased to put together a really, really good panel. So I hope you guys will enjoy this. What we've decided to do, there's a lot of content here. We're talking about architectural alternatives, 3 different versions for AMI 2.0. So I'm going to ask that we hold your questions to the end. Make sure everybody has a chance. I'm going to be timekeeper today. I've let these guys know because I know we want to get to the Q&A part and let each of them have a chance. So I'll do the introductions actually in reverse order. So our final speaker is going to be Daniel Robertson. He is Senior Director for Global Technology Innovation at Landis+Gyr. So very pleased to have Daniel here with us. The middle speaker will be Fabian Pettigran. He is with Ubic. He's the Chief Technology Officer, and they have a great amount of experience with running, not just selling equipment, which they do, and designing equipment, but also running an AMI network. So I think that'll be interesting, over 1 million meters. And then our first speaker, who will come up here in a moment, is Christian Ferreira. So Christian is with Easy Metering. He is the Mobile Network Director. And without further ado, Christian, please come on up.
Good afternoon, everyone. Thanks, Bob, from Select Spectrum, for inviting me to be part of this technical discussion to represent Easy Metering, to share with such distinguished participants. To get the most of our time, let's get started. In the first slide, let's look at the current challenge and gaps that AMI 1.0 presents. As these systems are becoming obsolete or reaching the end of their life cycles, utilities are facing increasing concern about longevity. This is pushing the need for AMI 2.0, which is future-proof and offer longer-term solution to avoid costly replacement. One key challenge is the increased demand and the complexity of managing DERs, which have now become critical for the future of the grid. Utilities need systems that can efficiently manage these new sources of energy while maintaining grid resilience and reliability. Additionally, AMI 1.0 lacks real-time operational data, which makes it difficult to optimize grid management and handle the demand of the modern future utilities. Interoperability and open standards are also a major issue. As many systems are proprietary, limiting utilities' flexibility by locking them into specific vendors. AMI 1.0 systems were not built to handle the complexity of DER, nor did they prioritize security against evolving cyber threats. Utilities will be able to address these challenges through advanced analytics platforms that can process large amounts of data. And finally, customers are getting more engaged about their energy usage, requiring real-time data and pricing information. Now let's dive into the transition to AMI 2.0 and its key component and concepts. AMI 2.0 introduced future-proof technologies with open standards for hardware and software, ensuring that meters can operate longer, adapt new third-party applications, and prioritize survey security to protect both customer data and grid integrity. Edge computing and distributed intelligence are essential advancements in AMI 2.0 by processing data locally, closer to where it is generated, rather than sending to a central server. These systems improve efficiency, reduce latency, and allows a smart meter to make autonomous decisions at the network edge, enabling quicker response to grid issues. AMI 2.0 generates vast amounts of operational and real-time data. Peer-to-peer communication play a key role here, and it's allow meters to exchange information directly, supporting faster decision-making at the grid edge. To manage this data flow efficiently, an advanced network architecture with open standardized communication protocol is required. Private cellular network like private LTE meets all of these needs. Now let's observe the next generation AMI 2.0 leveraging LTE low power wide areas, such LTE Cat-M and LTE NB-IoT. A key advantage is the extensive range and coverage. NB-IoT has 30 to 40% higher coverage range, and LTE Cat-M 15 to 25% compared to standard LTE, as we can see in the picture. As one of the key advantages is to support thousands of devices per square meter, the ability to greater device density, which is essential for large-scale AMI deployments. In terms of device costs, the reduced hardware complexity combined with low power consumption made them more economical compared to standard LTE. This technology also operates in licensed frequency standardized by 3GPP, which guarantee higher reliability and security. And they are recognized as future-proof technology by 3GPP. In the release 17 was introduced RedCap, the reduced capacity, ensuring the growing demand and massive IoT deployments. Some technical details: mobility. LTE Cat-M support mobility and handover. NB-IoT is designed for stationary devices. Talking about latency, with LTE Cat-M, we can have 15 to 100 milliseconds, while in NB-IoT technology operates in 1.5 to 10 seconds. Bandwidth, LTE Cat-M is in 1.4 megahertz, and NB-IoT in 180 kilohertz. Lastly, it's important to note that low power wide area chipsets ecosystem currently support frequency up to 2.1 gigahertz. Now let's move into one of AMI 2.0 use case: energy balance and demand response. AMI 2.0 allows utilities to balance energy loads more efficiently, detect fraud, identifies issues like overload or transformer inefficiencies. These systems also support demand response, enabling utilities to remotely control appliances and reduce loads during peak periods, preventing blackouts and optimizing grid performance. Here in the slide, we can see that we have new concept. In front of the meter is a communication, direct communication, peer-to-peer communication between the residential meter to the controller or the transformer meter. Here, the meter have multi-communication routing. They can speak directly to the head-end system, but the meter can speak to the peer-to-peer, device-to-device. You have two options. You can use private LTE to have device-to-device communication, or, for example, in urban areas with high density, you can use Wi-Fi as the communication. And we have the concept of behind of the meter. In this case, the residential smart meter is talking with the DRs, is talking with the EV charge, with the solar panels. Processing and data compression play a key role here to avoid to send amount of data to the central servers. The key point here is to analyze locally the data and processing locally. And finally, we can see two use cases. In the first side, we can see that for urban areas or high density areas, we can have direct communication to the head-end system, but the meters can speak between each other with Wi-Fi mesh. And the second use case is for rural areas with hard-to-reach areas where Wi-Fi mesh is not a good option, so they can use private LTE with LTE Cat-M technology or LTE NB-IoT technology to talk with them. By offering both scenarios, we can meet the specific needs of different environments, ensuring that AMI 2.0 can be implemented efficiently regardless of the region. No single solution fits all. By leveraging private LTE with low power wide areas technologies, utilities can choose the most appropriate communication architecture based on their operational requirements. Thank you.
Thank you. Wait. How do you make that work? Just. Oh.
You managed to turn it off?
Is that mine?
It's yours. Can we put it
Yes.
in? It's not really in slideshow version. Is that possible?
Who is playing with that?
I don't know. Who wants to? Trying to
Sorry.
get it in the presentation mode.
What up? Did I press the wrong button?
Yeah, you can press that's
This
the
one?
shadow button. So yeah, you just go down here and then you just click that. You got a little guy down there.
So
All right.
he wants the forward and back button.
Yeah,
right?
yeah.
Those
Just
two,
go
yeah.
right and left.
Yeah, yeah. Sorry about that. Yeah, so I'm Fabian from Ubic. So as Bob was mentioning, so we are an equipment vendor, but we are actually, maybe I'll take that microphone off. Right?
Sure. You can use this one if you'd rather.
Yeah, that's fine. Yeah, so we are. We are an equipment vendor, but we also come from the AMI background. So we do run a 1 million meter network in Taiwan, actually, with about 2,000 base sites, base stations. So we actually come in that space with the knowledge of what it takes to run a network for utilities and trying to develop products that fit the needs of utilities. AMI, so there is a clear trend to move AMI to private LTE. Now, traditionally, AMI has been run predominantly on proprietary or mesh technologies in the unlicensed band, and there is a clear trend to move to private LTE and 3GPP family of technologies. So it's been covered a little bit already. You have different options in the 3GPP LTE family of technology. You actually have the traditional LTE, Cat1, Cat4. You do have Cat-M1 or LTE-M, which has been introduced in release 13 and actually lowers the cost of the endpoint, simplifies the hardware design, and provides some feature to extend the coverage and reduce the power consumption. And then you have NB-IoT, so Cat-NB1 and Cat-NB2 that also been introduced in release 13 and improved in release 14 that provide actually even lower power consumption for endpoints that require even lower power and smaller amount of data, like water meters or gas meters. Now, when we talk about electricity AMI, it's been described many times already that the traffic for AMI 1.0 is already significant and is increasing exponentially when we move to AMI 2.0. And the traffic for AMI is actually one of the worst case type of traffic for any wireless network, in the sense that it's sending small amount of data and frequently enough from a large number of nodes. And typically those nodes also want to communicate all at the same time. So it makes it actually challenging for any wireless system to cope with that. LTE technology have introduced CADM1 and NB-IoT to deal with that, but it still comes with its challenges. So what we want to bring the attention of the audience to is that actually even moving to 4G and to 5G in the future, which also includes CADM1 and NB-IoT, there are challenges to cope with that traffic. And the reality is that the spectrum available to utilities is not infinite. So the spectrum is a scarce resource and is an expensive resource. And to deal with the traffic generated by AMI, you actually do need to look at the detail of the implementation of your network. So as described, many of the license spectrum options available to utilities are spectrum of 1 megahertz for the band 103, 3 megahertz for the band 106, 5 megahertz for the band 54. So those are not the same type of bandwidth that are available on traditional carrier networks, which typically run on 20 megahertz. So actually the flexibility and capabilities of those networks will be more limited, and we need to bring people's attention to the fact that there are some constraints that you need to work with when you deploy your network. So actually what we also want to point out is that when you have a limited amount of spectrum to deploy a larger and larger number of devices with more and more traffic, you do have to make trade-offs. So we talk about CADM1, for instance, that can deliver longer range thanks to extended coverage. It can also deliver lower power consumption. And the thing is that it cannot do that all at the same time. So you do need to make trade-off when you deploy your network, whether you design for coverage, whether you design it for capacity or for reliability, and even it's a LTE technology. That's not a silver bullet. You cannot have everything at the same time. So when you want to increase capacity of your network for the AMI type of traffic, typically you will have to go the route that has been typical for wireless system, will be to have a more distributed type of network. So, traditional AMI network have been mesh networks. You have some collectors that are spread across the cities and the territories. And moving to private LTE, the tendency will be to build big, expensive sites to get your coverage with your licensed spectrum, because building those sites is expensive. But the reality also is that when you get that coverage and large coverage, you will run into capacity problems. When you run a spectrum of 3 megahertz, even 5 megahertz, you need to realize that you cannot have more than maybe 100 devices communicating at exactly the same time, no matter what type of equipment you build. So if you talk about smart meters, that would be thousands, if not tens of thousands, in the range of that base station, you will run into challenges, into congestion and collisions, and you will degrade your power consumption, you will degrade your coverage. So what we think is actually a better architecture for the network is to use a more distributed network. So when you want to build capacity, there is either adding spectrum and more power, or you build actually smaller sites with smaller coverage area, and you can reuse your spectrum geographically. But in order to do that, you obviously have to reduce the cost of each site. So we actually encourage utilities to look at slightly more distributed type of deployment, even for private LTE. So you could say that the current approach for private LTE are big, expensive sites and direct device to the cell. And that's actually one extreme. And the other extreme is, well, you can say what is currently existing with mesh networks and even smaller and smaller mesh with the traffic increasing. I guess Tanya might cover that in a minute. And we think actually the reality and the optimal point is somewhere in between. So for private LTE network, for AMI type of traffic, you should use a more distributed type of network. And as it's been covered before, some of the traffic does not need to go back all the way to the head-end system or to the ADMS. Some of the traffic might be more local. So who says more local, distributed energy resources should come with a more distributed communication system as well. So the traditional carrier approach to deploying large sites to get your coverage actually is the fastest way to get coverage, but you will not necessarily have the capacity. So this might be suitable for some type of use cases where the number of endpoints is limited, teleprotection, some point-to-point links. But when you look at AMI type of traffic, then you will really have to consider the limitation imposed by the bandwidth available and the technology being used. In addition to that, a lot of those spectrum options are FDD, so we talk band 106 or band 103. And the reality is FDD has allocated the same amount of spectrum for the downlink and for the uplink. Traditional mobile use cases for users have been heavily downlink driven. We download stuff more than we upload, although this trend is a little bit changing with time. But utilities use cases and AMI are heavily uplink dominated. So the traffic is mostly in the uplink direction. Of course, you have downlink traffic, you have acknowledgement, you have on-demand commands, but the largest majority of the traffic is uplink, and the cellular system are already by design uplink limited. So it's the uplink path that will break first, not the downlink path. So this is really calling for a more distributed approach to cellular networks for utilities, especially in those bandwidths. And we also encourage to look at the different options for spectrum. While we talk about the band 54, for instance, which is a 5 megahertz TDD band, and that we think is a suitable option as well for that type of traffic, because TDD gives you the flexibility to bias your network towards more uplink or more downlink or 50-50, because TDD actually has this, you have a few configurations to choose from, and you can actually generate your network such that this band will be used 80% for your uplink and 20% for your downlink, which is very suitable for utility use cases and makes you make better use of your spectrum. So yeah, we essentially encourage the audience to look at the fine details of private LTE, because LTE and 5G moving forward to 5G is still a portfolio of technologies. So legacy LTE, LTE-M, CADM1, and NB-IoT have fairly different characteristics. They all can deliver some amount of throughput, coverage, latency, but you have to work within the envelope of that. And if you optimize, as I described, for coverage with CADM1, you lose capacity in terms of how many endpoints you can deal with. And it's important to be aware of those limitations when you make your spectrum choices, your deployment option. And that's why we encourage to look at different spectrum options that have some pros and cons for different type of application. So I don't think I have, I have some more slide on the on the more distributed type of deployment for AMI. And another point I was also making is that cellular technology was described. So you have the base station and you have what's called the core network that sits usually and traditionally in a central server. Now the core network is what manages the mobility of the devices when you do handover. So when you do a voice call, you move from one base station to another. You want to have a seamless transition of your voice call, and that's managed by the core network. Now we also have to look at actually utility use cases and AMI, so CADM1, NB-IoT for fixed assets. Those assets are not moving, so there is less need for having a central core network. So to be able to use the data at the more closer to the edge and to build some resilience and robustness in the network, we also encourage to look at more distributed option also for those elements. 3GPP technologies allow you to move the different element of the network where you want. So it does mean you can run some element of the core network directly in those base stations and those sites to make the data available more locally. And you know, what you sacrifice with that is the support for mobility, which doesn't exist in NB-IoT for AMI, for instance, anyway. So we also encourage people to look at the different network architecture, how you deploy your base station, your core network, to suit the needs of the utilities better, rather than just copy and paste the models that carrier have been using for the consumer and mobile world. So I think that's my take on it. I don't know if I have more slides. Oh yeah. Yes. So that's a different spectrum option. And yeah, the point I wanted to make on the spectrum as well, and we provide some equipment, for instance, for band 103, so which is a 1 megahertz band. So it actually supports only NB-IoT. Many utilities have this band already. It used to be the upper, well, it still is the 700 upper block A that traditionally has been used for point-to-point or point-to-point networks. It is now part of the 3GPP family of bands, so it's band 103. And NB-IoT actually can also deliver decent capacity, coverage, and even throughput when you deploy your own private network. So band 103 is 1 megahertz. When you deploy a network that is using 1 megahertz for NB-IoT, it does mean you can run multiple carriers. So you actually end up having a very interesting capacity, and that's a very good supporting band for AMI type of use cases. So people might have in mind that NB-IoT, yes, it's slow and it has some capacity limitations. That's very true. But it also because when it's used on public network, you have only one carrier that is made available for NB-IoT typically. But when you run that in your private network in band 103, you have 9 carriers to choose from, and you can have a much higher capacity and much larger number of nodes that you can deal with in that band. So we think that's also a very suitable band for utilities, even though it's NB-IoT only. Actually, NB-IoT is still a very capable technology, not just for very low type of traffic like water and gas meter. If you have sufficient spectrum to dedicate to NB-IoT, it's very suitable to electricity type of use cases, even moving to AMI 2.0, as long as you deploy that and you use that resource efficiently. So, yeah, that's the last point I wanted to make. I think I'm out of slide, right? No? Well, it's okay. I'm done. Yes. Well, yeah, so that's what I was covering. So actually, you might have some preconceived idea about what CADM1, NB-IoT, or Legacy LTE can deliver, but you actually have to look more into the details. You know, NB-IoT could be very slow if you use a lot of repetition to have a best coverage extension, but it could also deliver decent latency, but then you have to give up coverage. So it's all about trade-off. And it's not because it's called 4G or 5G that you don't have to make any trade-off or that the capacity is infinite. So you do need to look at the fine detail and fine prints when you deploy your network. And I encourage people to look into that before they go into the implementation and deployment phase to see how they will best use their spectrum and the multiple spectrum options, which could be complementary. So with that, I think, well, yes, I think I'm done. Thank you.
I think
those are my slides. No, where are your slides?
do we have missing slides? So I apologize.
Thank you.
I hate to see what slides. I can.
My eyesight is not.
Feasible to make this bigger on the screen?
My eyesight's terrible.
That's okay. I can dig and get it, but it's going to take a minute. Just run with it.
Can you hear me? Can you hear me? Hi, everybody. My name is Daniel Robertson. I work for Landis & Gyr, responsible for our global innovation strategy. We are a global company. We have about 400 million endpoints under management, so we're pretty large scaled. Here in North America, we're primarily known for our grid or Gridstream RF network. It works on the 900 megahertz ISM band. It's unlicensed. We're also developing we have developed a Wi-SUN solution that is standards based. Works on the same kinds of bands. So we are known for RF. We are known for our mesh networks. I joined the company about 8 years ago, and I was tasked to work on a cellular strategy for us. We developed cellular type devices, starting with Cat M1 and NB-IoT for metrology. We developed LTE as backhaul for our RF routers and gateways. In the future, we're looking at RedCap and enhanced RedCap. That's 5G new radio technologies. We're looking at non-terrestrial networking. So we had these technologies. I think when we first looked at the strategy, we thought they would be competing against each other. We thought the customer would choose one or the other. Actually, what we found was a preferred deployment actually is a hybrid deployment. What that means is a traditional RF network in the field with a mix of cellular endpoints. So we have mesh plus cellular hybrid deployments. The reason why that became very popular was because we found that adding quite a small amount of Cat-M, for example, electric meters, reduced the router count from 40 to 70%. That was very unexpected. So what that means is the cost of deploying and running infrastructure has been cut dramatically for an RF network. That's very surprising. The other benefits there are time to market, time to deployment has been sped up significantly. I know that there are other benefits. I mean, what that looks like in the field is you deploy a gateway. You can hang off typically 2,000 to 3,000 endpoints. But in many situations, you don't have that many endpoints. But you have to put a gateway there. So now we just drop in cellular. Solves that problem. So that's become very much a preferred solution for us. Kind of unexpected, but a very interesting learning point for us. We've extended the number of devices that support cellular. So electric meters on Cat-M. We have gas, water, and heat devices on NB-IoT. Gateways and routers typically on Cat4 up to Cat12. Streetlights and EV chargers and network bridges on a mixture of those cellular technologies above. One decision we got right at the start was to make our back end, our head end systems, our management systems, all network agnostic. So we took our Gridstream head end system, for example, and we created an abstraction layer that let us put cellular on top of that. That's very useful because it means we can add new technologies just by extending that extraction layer. We have developed a cloud solution for our back-end systems, and that's agnostic as of day one. I think another point on being agnostic, I would say when I first joined, we used to push and promote our RF technology with our meters. We don't do that anymore. You buy a meter, what kind of technology do you want? We're quite flexible now. We're not incentivized to sell RF. So yeah. Next slide. That works. So we joined UBBA when it first, in fact, the first meeting I went to UBBA was at DTEC. It was before the first dedicated UBBA meeting. We attended that, see what was going to happen. And that got us interested in support for private networks because there seemed to be some demand in the utility space for private networks. The comment there, multi-purpose network of networks, that comes from some of the early customer adopters of this who had existing networks of different types who said we want one network that does everything. Because we were agnostic in terms of technology, we thought, okay, we can get into this space, and that's where we've got to. Some of the benefits I think everybody knows of private networks is a bit like dedicated RF networks. You have control of performance. You can put coverage where you need it. You can add capacity where you need it. in terms of future readiness, if you deploy a cellular network, in terms of your upgrade path, it's up to you. So if you want to deploy a 5G new radio, G Node B from day one, go ahead. Point on interoperability testing. This comes back to the UBBA membership. Every time I've spoken at UBBA, I've always said the same thing, that don't just try and buy a meter from us and then expect it to work. It needs to be tested in terms of interoperability. So we have our equipment at just about everybody else's lab in terms of the infrastructure providers. And the idea there is we will manage the testing for you customers. So partnering is really important. And then UBBA is a perfect mechanism for that. And when we talk about drivers for adoption, customers, partners, suppliers, there's always, I find, a struggle here in terms of how do we make sure that we don't have a disconnect. And what I mean by that is, typically when we sell to utilities, we sell to their metrology departments, and then we find out later what they want to do. So the comms departments aren't necessarily speaking to us at the same time. So customers come to us later in the day and say, "Oh, we'd like to do some interesting stuff with your meters." Or actually, the worst case I get, and I still get it, is I didn't know your meter supported, 800, 900 megahertz, 700 megahertz, whatever. So CBRS, they don't know that. So I think that's always a frustration for me personally, is not being hooked up to those discussions, because I think as a company we still try to sell hardware first, and I think we can do a better job there. So in terms of interoperability, it's about testing, it's about certification, it's about doing POCs, it's about doing field trials, and the customer shouldn't have to manage that, in my opinion. I think that's across the ecosystem, or it should be. So onto this topic of AMI 2.0. My first comment on that is it's here. For us, we're launching this new product, this Revelo meter. It's shipping in February. We are doing samples today. The other thing I would say is we are developing commercial apps already. And we're working with customers, partners, to deploy these apps right now. I'd say National Grid is probably the first customer of ours deploying. They're deploying the Sense app. So Sense app is an application. It's a solution that you fit in the panel. It monitors inductance using couplers. It costs about $300. We've taken all that hardware, and it's now an app. No hardware cost. It's built into the app. So the kinds of use cases that we see with AMI 2.0 is, the first application is load disaggregation, and that's Sense, let's face it. So what Sense does, it can monitor load within the home. It can identify what that load is. So if you're looking at power consumption, it will identify what the key loads are. It will identify any kind of vampire loads in there, which basically are kind of parasitic and you didn't even know was there. It can actually identify faults, like wiring faults, hot socket issues, refrigerator compressor type problems. With this meter, we have this high resolution sampling capability up to almost 15 kilohertz. So we can do kind of high resolution voltage, power quality. We can do phase identification, obviously outage notification. But these applications, we have a suite of applications in an app store that we've built. But these can be developed by customers, or they can be built by partners of ours, developers. Some of those considerations that are brought from an edge perspective, because this is a grid edge device, is analytics. We can do analytics on the edge. We can do AI, ML, not at the edge, but in the cloud. But that introduces challenges. So edge to cloud is something we need to consider. The capacity within the device, there are certain use cases that use a lot of RAM or a lot of flash that needs to be stored. There's issues with latency, and that obviously comes down to the type of network you use, because we do high resolution here. And then, of course, there's potentially huge amounts of data. So from a network perspective, it's back to the types of network, types of technology you're using. So certain applications, NB-IoT is as well suited. That's probably similar to an RF type deployment in terms of constraints. But what you can do, and it depends on what you want to do. For the Sense app, we use Wi-Fi. We use the customer's Wi-Fi network because that's a huge amount of data that's been analyzed, most of it in the cloud. So we need something like Wi-Fi there. There's obviously issues that come from that in terms of permission and support and configuration. Cat-M is another option there. And in some cases, LTE, full-blown Cat4, Cat12 or something might be required, or even CBRS. We actually developed a prototype for a customer that used CBRS in one of these form factors just to prove that we could get it working, but fitting 4 antennas and things like that was a problem. The cost of the module was a problem. But potentially in the future, RedCap or enhanced RedCap could be an option. But as I said, it depends on type of application. And some of those use cases above, NB-IoT would be useful or would be suitable. And battery endpoints is another example of that. So network resilience is really important. So we've increased the amount of observability that we have down to the network in terms of being able to monitor performance, be able to do troubleshooting, that sort of thing. So AMI 2.0 is introducing more. It becomes more significant, more important. So the connection is more important, and how you manage it becomes more important. And the point on economics really comes down to CapEx versus OpEx, really. So the technology that you put on the device, the type of processor you use, the type of storage that you have adds to CapEx. But obviously, if you were to run everything over a cellular network and you do a lot of data backhaul, then the cost of data goes up there also. Private networks obviously help with that. But obviously there are constraints. So if you're on your own private network, then the cost of data is really more of a CapEx type of issue. So to the diagram here, that's our new Revelo meter. It's a grid edge device which has an ecosystem around it. You have a development studio. You have an application marketplace. There's an app manager built into that. We provide training. We supply support. We supply partners going to help develop applications, or if the customer wants to do it, that's fine. As I said before, it supports RF, mesh, and YSUN, but also it's being launched with cellular as of day one. So yeah, we can see the head-end system there, which is agnostic to the type of network that's being used. And because we have a cloud platform, we can do analytics, and we are working on AI ML within reason. Some of the use cases at the bottom there is location awareness. If you want to know precisely where your meter is, it sounds crazy, but in some cases that's important. Power quality with the high resolution sampling. The registers within this device are pretty much from a CNI meter, so we have that kind of really high resolution capability. And voltage monitoring. We have a whole lot more applications that we can't really show here because they're being developed for specific customers, but it's a very capable device. And as I said, AMI 2.0 is here. The capabilities, the technology is here. Whichever network you want to deploy, we're agnostic. If you want to work on a certain technology, on certain spectrum, then it's a case of working with across the partner ecosystem. Because I even heard today, this week, that some customers had bought this and they were asking me, I didn't know that you could do that with it. So they bought the hardware and then they're trying now to figure out what to do with it. So it's basically about working across the ecosystem to get the most value out of these things. So, yeah, that's my last slide.
Great. Thank you. All right. Thank you, Daniel, and thank you also, Christian. and Fabian. We'll open now for questions from the audience. I have questions if you don't. So, but please go ahead. We want to satisfy your questions first. All right. Well, I'll get this started. The question I've been asking is, how much bandwidth does it take to handle AMI 2.0? And I think I've heard everywhere from 200 kilohertz to maybe 10 megahertz. So, do you want to address? Does anybody want to address that one? How much bandwidth does it take for AMI 2.0?
I think that's kind of it's a difficult question, but I mean the correct answer from my perspective is why don't you find out? Why don't we find out? Because it depends on the type of application. And my experience with AMI 2.0 started with Sense, and that was probably the worst case scenario in terms of the amount of data, the type of real-time requirements involved for safety. But what we found is as we started developing other applications, most of them didn't look like that at all. So if it ends up saying, well, NB-IoT isn't fit for purpose, well, it actually is. And is RF fit for purpose? Actually, they are, but it depends on the use case. But what I like about AMI 2.0 now is we can actually test it, we can prove it. We're not theorizing, we're not writing calculations or equations, we're saying, let's try it out with real customers. So.
Yeah, I will say it really depends. So to give some numbers, taking an example, we are running an AMI network, but it's with purpose-built technology, so it's not 3GPP standard. But it's AMI, you could say it's AMI 1.0, so it's 15 minutes load profile, and it's running with more than 97% of in-time delivery, meaning you get your meter readings within 15 minutes. And we run that within 1.2 megahertz of licensed spectrum. Reality is that when you move to LTE technologies, you actually have some more overhead compared to purpose-built technologies for AMI. So you will typically need more than that when you move to CADM and NB-IoT. But you also need to look at, moving to AMI 2.0, you might want to get down from 15 minutes to 5 minutes or even 1 minute. But there are fundamental question as well is, you want 1 minute reading, but do you want it every minute? Do you want it every 5 minutes? Do you want to be able to compress the data? Do you generate the data pushing the data from the device, or the traditional way of pulling the device, which is generating extra traffic for no reason, in a way, pure redundant traffic? So there are also many ways that the traffic of AMI can be optimized. Just talking data compression alone can give you a ratio of 5 or 10x on your data from your AMI meter. So, yes, so the question is, it varies a lot, and you need to look at your architecture, how you generate the data. But it's anywhere from 1 to 5 megahertz will be required if you use your spectrum efficiently to run a AMI 2.0 network. Will be my ballpark guess if you do things properly.
In this case, it depends of the size of the packet. As Easy Metering, we promote broadband communication. So we started Easy Metering as a broadband communication company, but now with the low power wide areas, we can fit in this use case. For example, with edge computing and with data compression, the meters can take decision locally. So the data that you need to send to the LTE network, it's just an alarm or just an event. So the processing is in the edge. So it's a very good point here because we can fit our technology to work with NB-IoT, with LTE CAT-M, and LTE standard as well.
Great. So other questions from the audience? So I'm going to start with Christian this time. So we're hearing the applications that can be developed, a wide range of applications. Do you have an interesting application that has been developed out on the edge that you think other people would be interested in? that really provides value either to the utility or to the end user? Interesting applications.
Yeah, actually, the use case of energy balance and demand response is a very good use case in AMI 2.0. So, using distributed intelligence, using artificial intelligence. So Easy Metering now, the new version of our technology is based in Linux. So we have more potential computing inside the device. So to provide machine learning, to provide artificial intelligence. So the idea is to give more value to the device, not just a meter for billing. Is to have a sensor in the network to help the utility to understand what is happening behind to the meter and what is happening in front of to the meter. Talking the residential meter talking with the transformer meters.
Feel free if you answer that one.
No, I talked about apps already.
What about surprises that you've seen? Now, we have now computers on the edge of the network sensing what's going on. Have you seen surprises from what you found in the home? Are there surprise ways to save energy? Anything along those lines that you comment on? No surprises.
We don't like surprises.
All right. Well, any last observations that any of you would like to make? Or questions? Last questions from the audience? All right. I think it's time to say thank you very much for enjoying.
Thank you.
Thank you for attending. Thank you, panelists.